Hi everyone, welcome to part 2 of lecture 9, and we will cover the log normal distribution in this part. So we can get a simple clue from the name of that distribution, which is a log normal distribution. That means logarithm of something will be normally distributed. So if we explain it in a formal way, we can say that a random variable x is said to have log normal distribution with the parameters mu and the sigma square if ln of it, the natural logarithm of the x, is normally distributed with the parameters mu and sigma square. And the PDF of the log normal distribution is this one, which is similar to the normal distribution PDF. Instead, we use ln of x instead of x in this part, in that power part. And also we added x in the denominator of this part. So the CDF, the cumulative distribution function, doesn't have a closed form formula, but still we can use the normal distribution table, the CDF of the normal distribution. Remember that we were using a table, and that denotes the CDF of the normal distribution. Instead of using x, we can use ln of x, and we can still use that table. The expected value and the variance of the log normal distribution is the expected value of x is equal to e to the power the mu plus sigma squared divided by 2, and the variance of the log normal distribution is e to the power 2 times mu plus sigma squared times e to the power sigma squared minus 1. So you don't need to memorize all these things, okay? Just if you need something, you can look at the different sources, or if you encounter in your exam, all these things will be given to you, okay? So note that if y is normally distributed, e to the y has a log normal distribution, not ln of y. Remember that we said that the logarithm of something will be log normal distribution, okay? And the ln of x should be normally distributed. So if y is normally distributed, then we can say that e to the power y has a log normal distribution. So the simple thing, if y is normally distributed, we can say that e to the y has log normal distribution. Also, if ln of x is normally distributed, we can say that the x is log normal distributed, okay? So let me write here, if y is, if y is normal, then e to the y log normal, okay? And if ln of x is if ln of y is normal, then we can say that y is log normal, okay? So keep this in mind, and don't be confused about the ln and e to the power, okay? So actually, the density of the log normal distribution can be derived from this point, and let's examine the CDF of the x, which is equal to e to the power y. So x is normally distributed. So the CDF of the x is the probability of x will be less than or something less than or equal to some particular value x, right? The small x. So because x is equal to e to the y, we can say that the probability of e to the y will be less than or equal to x is same. So we know that in log normal distribution, the x range between 0 and infinity. So it cannot take the negative values because the ln will be undefined. ln of negative something will be undefined. Okay, let's do that. Here, if e to the y is less than or equal to something, ln of this will be less than or equal to ln of the same thing, right? So if e to the y is less than or equal to x, we can say that the ln of e to the y is less than or equal to the ln of x. Okay, so that's why let's take the ln of this 2 guy, and that will be the probability of y, which is less than or equal to ln of x, right? And we start from the normal distribution, so that can take the values between minus infinity to ln of x, because that is given particular constant value. Okay, we have to accumulate all the probabilities between minus infinity to ln of x. That will give us, that is the how we derive the CDF, or how the CDF works. And that is the PDF of the normal distribution by substituting some parameters here. Let's say t, which is equal to e to the y. So dt will be equal to e to the y times e to the y dy. So here, instead of y, just write ln of t, because we just use t, which will be the new parameters. Okay, that's coming from here. That will be ln of t. So because if we take the ln of this t, these two things, that will be ln of t will be equal to the y. Okay, so that's why instead of y, we can write the ln of t. And instead of dy here, instead of dy, we can write d2 divided by e to the y, right? And we know that e to the y is equal to t. That's why, which is equal to dt divided by t. So instead of dy, we can write dt over t, and that over t is going to. Okay, so, and let's specify the new limits for the new parameters. That is for the y, right? And that will be for the t one. So in this one, the y ranges from minus infinity to ln of x. So if I put the minus infinity here, the t will go to the 0. So my lower limit will be 0. And if I put the e to the ln of x, remember that, which is equal to x. Okay, e to the ln of x is equal to x. Okay, so that's why the upper limit will be x. And that is the that is the my new CDF. Okay, I mean my new density. And remember that x is coming from this one. Okay, that's why we added one additional x to the denominator. Okay, but you don't need to memorize all these things. Just if you know the logic of the log normal distribution from here, and if you know that the expected values and variance, I mean, not knowing, but if you know, you need to check your resources to find the expected value of x and the variance of x. That's easy. You don't need to memorize all these things, but just try to understand the logic behind the log normal distribution, and please understand the relationship between the log normal and normal distribution. So you can find the different shapes based on different parameters. And by the way, in here, the mu represents the theta represents the mu, and this v squared represents the sigma squared. Okay, these parameters, this notation is used by your textbook, but we will prefer to use mu and sigma squared again. So by changing that parameters, you will be you will find different shapes. But remember that, that mu and that sigma squared is not the variance in the expected value of our log normal distribution. Okay, remember that in the normal distribution, that given mu and the variance is the actual expected value and variance of that distribution. But in this case, the given mu and the sigma squared is not the expected value and the variance of the distribution respectively. Instead, the expected value of the log normal distribution is this one, and the variance of that log normal distribution is this one. Okay, please don't be confused about this. Okay, let's look at an example to make it more concrete. So the lifetime in hours of a semiconductor chip has log normal distribution with mu 8 and the sigma squared 2.25. Again, this is not the expected value of the lifetime of a semiconductor, and that is not the variance of that distribution. Okay. And what is the probability that it will fail within 5,000 hours? Let's look at the solution and let t denote the lifetime. And since it's log normal with mu, which is equal to 8, and the sigma squared is equal to 2.25, we have a random variable x, which is normally distributed with the parameters mu is equal to 8 and sigma squared is equal to 2.25, such that t is equal to e to the power x. Why? Because remember that if t is log normal, then ln of t is normal, right? So what is the ln of t? The ln of t is actually something e to the the ln of t is something x, right? And t is equal to e to the x, and we know that we have x is normally distributed. So what we are asked, the probability of t will be less than or equal to 5,000 hours. So the probability of t will be less than or equal to 5,000. Instead of t, we can write e to the x because they are equal. And if e to the x is less than or equal to 5,000, that means ln of e to the x will be less than or equal to ln of 5,000. Okay, and this will give us the probability of x will be less than or equal to ln of 5,000. So we know that the x is normally distributed with the given parameters. So we can standardize by, remember the formulation, x minus mu divided by sigma. So x minus 8 divided by 1.5, which is the square root of 2.25. Okay, and also we need to standardize this guy, which is the ln of 5,000 minus 8 divided by 1.5, and that will give us probability of z will be less than or equal to 0.34. So to calculate this guy, this probability, we just need to look at the table we have seen before. Okay, so in that table, we will look at this value and we will get the corresponding probability. So the probability is 0.63 something. That means the probability of the lifetime that semiconductor will be less than or equal to 5,000 hours is 0.63 something. Okay, so this is how we can solve this kind of problem and how we can use the relationship between the normal distribution and the log normal distribution. So when is it useful? When is the log normal distribution is useful? The multiplicative central limit theorem, which is the products of independent identical distributed random variable approach to the log normal distribution. So if this is the case, the log normal distribution will be the log normal distribution can be used. Okay, so that's mean the ln of the x1 times x2 times until xn which is equal to ln of x1 plus ln of x2 plus ln of x3 until ln of xn. So we can use in this part, in this for this problem. That is actually if you want to give an example to this situation, the many natural growth process are driven by the accumulation of many small percentage change. So let's say you have established a new job and you are designing some products. In each step, you are improving your products, and in those each steps, maybe you will improve your products by a small percentage, but in each time, like you start from this one and you improve your products, let's say 0.5 percentage, and in other stage 0.3 percentage, and this whole process at the beginning to the final stage is the accumulation of the small percentage of the improvements, right? So this kind of things can be modeled by the log normal distribution. Also, there are many empirical cases that are modeled with log normal distribution, such as length of comments posted on forums and length of chess game, distribution of incoming population, city population, etc. So if you want to learn the details of when the log normal distribution is used, or it is better to use it, you can search or you can look at your the textbooks for much more details. To summarize, we can say that a process in which the improvements or growth is made by small stages, and accumulation of that small stages can be modeled by the log normal distribution. Okay, so let's look at another distribution, and which is the last special distribution in this lecture, is called the beta distribution. So a random variable x with the probability density function is said to have a beta distribution with the shape parameters alpha and beta. So in this distribution, the alpha and beta is both the shape parameters. So changing of this parameter will change the shape of the distribution. Okay, so we just seen that, which is the gamma distribution, and this part is similar to the uniform distribution. Okay, just remember it. If you don't remember it, please check the previous lectures. That multiplication is similar to the uniform distribution, and the x will range between 0 and 1, and both of them are included. So alpha and beta makes the PDF symmetric about the x is equal to 0.5. Okay, that's if the alpha and beta is same, let's say, which is the 0.5, that will be the symmetric about this point. That's mean this guy, that x, let's say 0.2, and that is 1 minus x will be 0.8, will have the same distance to this point. Okay, so and the region under this tanks will be the symmetric, the same. And the alpha and beta, if the alpha and beta is equal to 1, which is identical to the standard uniform distribution, so that's mean the under the region will the area of the under the region will be equal to 1. Okay, and the expected value and the variance, the expected value of the beta distribution will be alpha divided by alpha plus beta, and the variance of the beta distribution is alpha times beta divided by alpha plus beta squared times alpha plus beta plus 1. So again, you don't need to memorize these things, just try to understand the logic, and if you need, you can find these expected values and the variance from different sources. And in this exam, if you encounter a question, you will be given all this information. Okay, so again, by changing there's two parameters. You can have different shape of the beta distribution. Here, let me look at this one. The alpha and the beta is equal. That's mean here that that distribution will be symmetric about the 0.5, right? So here, that will be the symmetry. That's mean, right? One. This region here will be the same, okay? But it is possible to get infinite shape of this distribution by changing the parameters. So when it is useful, the first thing is to model the proportional or indices like the Gini index. The model proportion means that I will not give you the details of these things because you will see that in the statistic class, but just let me introduce briefly. Let's say you have some process and you know that the probability of success is constant but is unknown, and when you graph that process, maybe some of the piece will be here and some of them will be here, some of them will be here, and you can model this part, okay? So in other words, you can model the parameter of the model itself, okay? And if that is the case, you can use the beta distribution, or you can use it, or it is used for the indices like Gini index. That is, the Gini index is about the economy, but maybe you will see it in your the economic class, and that is the index to measure the inequalities between the incomes in a in a region or in a nation or something. In this case, that will be if that is the case, we can use the beta distribution to model such a problem, such an income inequalities problem, okay? If you want to learn the details of these things, you can I don't know if you take the economic class, but if not, and if you want to learn about this index, you can look at the different sources, and this is not about our class. Also, when there is no further information, the generalized beta distribution is used to model a random data, okay? Such that if B is a beta random variable, X will be equal to A plus B minus A times B has a generalized beta distribution. Remember that is similar to standard uniform distribution, right? Which range between 0 and 1. The random variable will range between 0 and 1. And let's say that is X. And let's say we have a new variable, Y, and that is ranging 5 to 10. So we can use this standard uniform distribution to generalize to this model. How? That is corresponds to A, that is corresponds to B, that corresponds to A, and that corresponds to B. So simply the B minus A for this one times X plus A will give us the Y. Okay, so that will be the generalized version of the standard uniform distribution. And here, that is the same thing. We can generalize the beta distribution. Actually, that beta distribution is not called the standard beta distribution, but let's say the standard beta distribution in a same way. Okay, but in this case, you need to know 4 different parameters. Which one? Is alpha, beta, and A and B. Okay, so you have to deal with that 4 parameters. That's why there's a famous quote here: with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. Okay, that is said by von Neumann. He is a famous mathematician. Okay, so another area that the beta distribution is used is called the program evaluation and review technique, which is PAT, which is also called PAT. So you will see these techniques in your further classes, but let me briefly explain what is this thing and how we can use that one. Okay, let me give you a concrete example, and you are a project manager and you are working to build a building, okay, or let's say a school building or another thing, the airport, something else. This whole process actually consists of different small stages, right? Some events, like the event A, event B, and event C. And let's say to be able to start the B events, the A should finish. So after finishing A, you can start B. And maybe to finish or to start the C, you have to finish B. So that's why some precedence relations exist in this kind of network, that project network. Sometimes the time needed for these events can be deterministic. That will be constant and that will be given to you. If this is the case, your job will be easy, right? Because you can simply calculate the total duration or total time needed to complete this project. But in general, these times are not deterministic, they are random. So if this is the case, we have to model what we need, okay? If this is the case, we can use the beta distribution to model such a project or such a event. How? When alpha is greater than 1 and the beta is greater than 1, we know that the mode, the peak of the density, if that's the graph, the peak point, or called the mode, is alpha minus 1 divided by alpha plus beta minus 2. Okay, so this is correct for all beta distribution in which alpha and the beta is greater than 1. Let me show that. Let's look at this one. Okay, in here the alpha is 2 and beta is 5, so that will be the alpha minus 1 divided by alpha plus beta minus 2, right? So alpha is 2 minus 1 divided by 2 plus 5 minus 2 will give us 1 over 5, which is 0.2. And the peak point is 0.2. So we can find the density of, the mode of this distribution by using this formulation if alpha and beta is greater than 1. We know that one, and if we can estimate the minimum, the mode, and the maximum B possible values of some random activity time X. So again, this is not in this case, in our, let's say in our project, the X is not ranging from 0 to 1, right? In the beta distribution, we say that the X will be between 0 and 1. But in the special case, let's say the X is not ranging between 0 and 1. Maybe it will range 0 to 5, something. Like imagine that project from, let's say the event A. Maybe it will take 2 days, maybe 5 days, maybe 6 days. So it will have some range, and probably that will not be between 0 and 1. So if we can estimate the minimum, which is A, the mode, and the maximum possible values of some random activity time, okay, if we can estimate these things, and assume that the expected value of X is equal to A plus 4 times M plus B divided by 6. So this is not always true. We just assume that. Okay, we just assume that. That's not always true. And also, one important thing here, how we can estimate the A, M, and B, minimum, mod, and the maximum values. The easiest way, if you are an expert in that kind of project, you can estimate this thing. If not, you are just doing the role of project manager, okay? And then you can ask to an expert, okay? Expert in that field. For example, you can ask a civil engineering if you are building something, okay? Then we assume that the expected value of x is equal to a plus 4 times m plus b divided by 6. We can model x, that new special case, with a plus b minus a times b, right? As we seen here. We can generalize that one. We can generalize the standard beta distribution, where b is a beta random variable with parameters alpha and beta. So remember that the b is the distribution. This one, the x will be ranged between 0 and 1, but in our special random variable, the range will change. That will not be between 0 and 1. That's why we are generalizing that beta distribution to another one. So which can be calculated solving these two equations. Okay, in this one, we know m, right? We just estimated it, and we know m, again we estimated it, and we know the b. So simply we can calculate the alpha and beta here, right? Because we have two unknown, which is alpha and beta, and also we have two equations. So we can simply find what is the alpha and what is the beta. So if we found these guys, we can simply calculate the generalized version of the beta distribution. Okay. Okay, to summarize, if we want to generalize beta distribution to another case, we can simply use these two formulations. Why? The peak of density is correct for any kind of beta distribution in which the alpha and beta is greater than 1, which is alpha minus 1 divided by alpha plus beta minus 2. And that is equal to the mode of our need case, and the mode of our need case is estimated by asking an expert, let's say. And also, we assume that the expected value of the distribution is a plus 4m plus b divided by 6. And that is equal to expected value of the beta distribution, right? Expected value of x. What is that? Remember that, which is alpha divided by alpha plus beta. So that will be equal to this one. And here we have two unknown, alpha and beta. And also we have two equations. So we can easily solve this one and we will find the alpha and beta. So what will help us? For the beta distribution, we know the alpha and beta now, we just solve it. And also we know the range, we just estimate that range. That means we can find the probability of any new random variable, right? What I mean, let's say, what is the probability of finishing the A event at 5 days, for example? So we can now simply calculate the probability of this event, and thanks to generalization of the beta distribution. Okay. So here the A events, let's say, ranges between 0 and 5, and we can simply calculate what is the probability of A will be less than or equal to 3. Okay. So we can now simply calculate this probability. Okay, that is end of part 2, and thanks for watching. We will continue with the moment generating function.